Good morning. Can you hear me? I can't hear you, Gordana.
Yeah, we can hear you. I can hear you.
There you are. Well, I thought last lecture was rather intricate and maybe somewhat difficult to follow. So I thought I would take a deep breath and try to.
Did you post it? I had a document.
No, I screwed up and didn't record it.
Oh, no.
Sorry. I could send you the, well, I'm going to post a typed version of it in the next day or so. And I could send you, if you want, the notepad that I have.
That would be great. Yeah, thanks.
I don't know how much, yeah, sorry about that. You know, when I go on early, I turn off the recording so there's not 10 minutes of silence at the beginning. And I have not yet remembered to turn it back on. And I told myself, never do that. But I did it last time. I thought, I'll remember. And I didn't. So I'm sorry. Anyway, I can send you the notes. I have your email address, right?
Yeah.
Why don't send me an email just to remind me, and I'll send you back.
Okay, great. Thanks.
Anyway, I thought I would take a breath today and sort of remind ourselves of where we're trying to head and why we're heading in that direction, and then review where we got last time, and then push forward to the theorem I stated right at the end of last time.
And I apologize in advance. I have to leave early today because.
Oh, I'm going to have to leave early today too. I have another Zoom appointment at 12:40, so I'm going to have to leave about 12:30.
I teach at 12:40 on Wednesdays.
Okay, well, we're perfectly in sync.
Okay, great.
All right. So we're considering, we have this space of functions, C infinity functions of V cross I to the interval with various conditions. They send the bottom to 0, the top to 1, and they send the interior of V cross I to the interior of I. And there are no critical points on the boundary. And inside there, we have E of V functions with no critical points. And what we've got to show is that E is path connected. So equivalently, since F is contractible, that paths in F of V with endpoints in E of V, there's only one homotopy class, which means that given any path in E, path in F with endpoints in E, it deforms to a path in E. And we showed early on that this is equivalent to the pseudo isotopy theorem. So that's what we're studying. We've now shown that there's an open subspace, F naught of V union F1 of V, indicates the stratification. So F naught of E is an open-dense set of Morse functions with distinct critical values. With distinct critical points have different critical values. F1 consists of crossings of critical values and cusps, where two critical points are created as you move along. So crossings and cusps, those form the codimension 1 strata in here. And our path, any path gamma in F with gamma naught and gamma 1 in E, so any of the kind of paths we're considering can be approximated as homotopic by a small deformation, rel endpoints, to a path gamma naught 0, 1 into this F naught union F1. So this path is a Morse function with distinct critical points, distinct critical values at the critical points almost everywhere. Finitely many places, you either have a crossing where two critical points suddenly have the same critical value, or you have so these things consist of crossings and creations of bursts or the opposite deaths. Okay, so you have this path. This is in E of V, no critical points. This is in E of V, no critical points. So there's finitely many values where either there's a crossing or a node is created, a birth is created, or the opposite, a birth dies, which is a death. I mean, two critical points cancel each other. So we have this graphic that we've talked about. This is the parameter for the curve. And this is the height function, T, just given by the projection of V cross I to the interval. And then we can look at all the critical points as we, the critical points for the function gamma S as we move S. And generically, we get some finite set of points with distinct critical values. These move along, they cross, suddenly they're nodes, more crossings, and we get a graphic completely contained in the interior, because there are never any critical points on top and bottom, and we begin and end without critical points. And our object is to somehow use this graphic to use the graphic and find moves that simplify it, arranging things and so that the critical points are ordered by index and then starting to cancel them until we can get rid of the graphic by some moves. The problem is the graphic leaves a lot of information out. So the graphic does not contain all the necessary info, because all you're recording about the critical points is their heights. You said nothing about where they are in the V direction of the manifold. So the V direction is completely missing. So you can't just look at the graphic and say, okay, well, I see some configuration in the graphic, so I can make a move, canceling things or shifting one branch past another, because you have to know what's happening in V in order to do that. So the point is to understand the basic move here is the crossing, because the nodes, the births and deaths, are completely local operations. And we understand them, we have a model for them locally. There's a unique model. So what's really harder to understand is these crossings, because they involve moving the critical points around, and we're watching how they move in the T direction, but we have to understand how they move in the V direction as well. So we need some geometric information that captures the crossing paths up to homotopy, relative various endpoints and so on. And in particular, we're studying the objects that we're studying right now are called descending paths. Which turn out to be the sort of crucial ingredient. So these are paths where there's one critical point which is distinguished, and maybe lots of other critical points, but nothing happens in this part of the path except that this critical point interchanges its height with some collection of other critical points. So we have this is our path of functions going this way. It's going to be a subpath inside the full path. And during this part of the path, there's no bursts, no deaths, and only one critical point that crosses others. The others may move up and down. They can shift as they go along, but they don't cross each other. And this critical point crosses some sequence of them. Okay. Called the descending path, and we want to understand all descending, we want a geometric information to capture all descending paths up to homotopy, and the geometric information is a descending disk from the critical point, the special critical point that's doing the moving, C naught, that passes some number of lower critical values. So this is not a path in the two-dimensional graphic. This is an object in V cross I. It's the descending manifold out of this critical point that we're talking about having shift positions. And this is just, we've just got one function here, and this is its descending manifold. Here are the other critical levels that we're going to pass. So these are the critical levels. And these descending manifold, together with the levels that it passes, are produced for us an elementary, what's called an elementary descending path. And the theorem I stated last time was elementary descending paths that cross a certain number of critical values. The space of those up to homotopy type is the same as the space of the descending manifolds out of this critical point that cross that many critical levels. Okay. So that doesn't get us all the way.
John, can you please repeat that statement again?
Yeah. So the theorem I stated last time, and I will restate in a minute, is that if you look at what I call elementary descending paths, and I'll describe what those are. They're a special, very constrained type of path. I showed the space of those coming out of, the space of those that does this is homotopy equivalent to the space of descending manifolds that cross the right number of levels, descending disks that cross the right number of levels. Now that's only, we're trying to build a bridge between geometric objects and these paths, descending paths that cross these general descending paths about which I don't have much information. I need some bridge between the homotopy theory or connected components is really all I care about, of the geometric objects and the homotopy classes of these paths. The geometric objects are these descending disks for some gradient-like vector field. The paths, well, we're building a bridge, and this bridge is, we're going to build like you often build bridges. We're going to start from each bank and build outward. So the theorem that I stated last time, and we'll restate and then prove, is we get to elementary descending paths. So a special category that are closely related to these geometric objects of descending disks, and we have a homotopy equivalence between the space of those paths and our geometric objects. And it's a completely different argument, and a much simpler argument actually, to build the bridge the other way, that any descending path is homotopic rel its endpoints, rel its initial point, to an elementary path. So in this way, we see that these paths that let the critical points move around but not cross each other, except during the path C0 crosses these three, they can actually all, up to homotopy, given the initial point, they can all be constructed by taking a coordinate system, a local Morse coordinate system around the critical point with a descending manifold, and using this path, elementary path that goes with that coordinate system, so that in fact we have a very good understanding of what all these paths look like up to homotopy fixing the initial point. And once we have that, we then will be in a position to do all the moves to simplify the diagram. So this is really the core of the argument. So let me state the theorem that I stated at the end of last time. So we're considering embeddings. So our model, MR, is in Euclidean R space, cross Euclidean N minus R space. This is one of the Morse models. We have coordinates X and Y here, an R tuple and an N minus R tuple. And MR is given by the inequalities -1 less than or equal H of X, Y less than or equal to 1, and K of X, Y less than or equal to 1, where H is simply the standard Morse function, and K is a product of the norms squared of X and Y. Okay, so this is one of our standard Morse neighborhoods. This will be the point 1, norm 1 in X. This is the point norm 1 in Y. There turns out to be a nice point. It's the golden ratio for the X coordinate, the norm of the X coordinate, and the sort of conjugate for the Y coordinate. And this is the opposite. And this is the flows, gradient flow lines here. And this is MR, or rather its projection into norm X, norm Y. So P is the space of embeddings of MR into W adapted to our function F. So F is given. It's a given Morse function. Well, it doesn't have to be a Morse function. Adapted to F at a critical point C0, which means we actually have a diagram. We have a smooth embedding. Phi of the critical point here goes to C0. And this has to send levels to levels in the sense that when we take H, which goes down to -1, 1 on this side, and F, which goes down to 0, 1 on this side, we have an embedding called phi prime of the domain of H to the domain of F. So this is a commutative diagram. In other words, it's a model for F, a Morse model for F, This is the standard Morse function in some neighborhood of the critical point. And we need, well, so once you have P is a space of embeddings, actually I'm going to restrict those in just a minute. I'm going to require that phi prime of -1, 0 crosses some fixed number P critical values. So I'm interested in moving past P critical values, or in this picture, the descending disk should extend past P critical values. Well, if you have an embedding like that, then the standard descending disk in MR goes to a descending disk for F that passes P critical levels. So we're looking at embeddings, the space of these embeddings, and we're going to fix P and always require that. I won't put it in the notation. So this is the space of embeddings like this, adapted to F at the critical point C0. So 0 goes to C0. You get a nice commutative diagram. Levels here go to levels here. And the descending manifold of the standard descending manifold for the model goes to one that passes P critical levels. And then I defined the elementary descending path H lambda to be H minus epsilon, some fixed small number, lambda times W bar, where W bar, just to remind you how I did it, how surf does it, W bar is W of H, W of K, where W is a function that support is -1, 1. C infinity function, support -1, 1. W of the origin is 1. And the derivative W prime is negative on 0, 1. And the second derivative vanishes at the origin. So this is a family of Morse functions. If epsilon is sufficiently small, then the only critical point for F lambda, for any lambda between 0 and 1, is the origin. And the value, of course, F lambda at the origin is minus epsilon lambda, because omega bar at the origin is 1. So given this embedding, phi of MR into W, we get, first of all, we get this descending manifold. Phi of the standard descending manifold passes these critical levels. And we also have a path of functions, H lambda. Because the support of W bar vanishes when H is equal to, well, since W bar is infinitely, since W bar has support contained exactly in MR, you can use this path to construct a path of functions F lambda from 0, 1, using the same embedding at each time down here. So these functions F lambda, when you restrict them to the image of the model, you get exactly this path H lambda, and outside F lambda restricted W minus phi of MR is F. It's a constant path outside. So this path is supported exactly on the image of M. And if the descending manifold passes all the critical levels, we can take phi without changing the image, just operating by a self-diffeomorphism of M, we can take phi such that F lambda passes the same however many P critical levels. Okay, so even though it looks like we're restricted to functions that don't move very far, because you only move the critical value from 0 to minus epsilon, we can shift the where minus epsilon goes by a self-diffeomorphism of MR that shifts the levels way down, and we can get the ending of this F1 of 0 to be arbitrarily close to the boundary of this descending disk. So this is the way that embeddings give elementary paths, which I'll denote this way, and embeddings give descending disks, which I'll denote this way. So this is the space of descending disks from C0. This is the space of elementary paths. So by definition, an elementary path arises from an embedding of the standard model like this, and the standard path of functions in the standard model. And these are both required to pass the P critical levels. I call this map rho, and I call this map, D. Okay. Now, I proved last time a lemma that says if you have two embeddings, phi and phi bar in P, and rho of phi equals rho of phi bar, theta and theta bar, sorry, well, switch notation here. So rho of phi is rho of phi bar if and only if there exists a G in the group I called G12. This is the group of self-diffeomorphisms of the model that preserve norm of x squared and norm of y squared. Okay. Well, if and only if there's a diffeomorphism like that, such that phi bar is phi composed with G. And that implies, as a corollary, if rho of phi equals rho of phi bar, then d of phi equals d of phi bar. Because if you operate by a function that preserves norm x squared and norm y squared, it preserves the locus where x is 0, which is the descending manifold. So it preserves the descending manifold in the standard model, and therefore it preserves the image of the, when you operate by this diffeomorphism to get a new embedding, you don't change the, see, I said something wrong here. If you operate by the diffeomorphism, self-diffeomorphism of M, and then go in by phi, since the standard descending manifold is sent to itself, the standing image under phi bar, the descending manifold will be the same as the image under phi. So there is a function across here, chi. That was our basic diagram, making this diagram commute. And now the theorem is Maybe before stating it, I'll say a little bit about the theorem is that after an appropriate modification of EL to make it a reasonable space, this map induces an isomorphism on homotopy groups. So this space, slightly modified to make it reasonable, is homotopy equivalent to the space of descending disks. The space of elementary paths that cross P levels is homotopy equivalent by this map to the space of descending disks from the critical point that pass P levels. But we have to do this modification of E. And I'll tell you why, and then I'll briefly give you the proof. Modification of EL. So the first thing, I can replace any space, EL or any of the other spaces, by a simplicial set, which is the singular simplicial set of EL. This is something you can do for any space. So maybe I should stop and ask, do you want a quick 5-minute, 10-minute refresher on simplicial sets?
Yes.
Or is that something familiar to you? I heard a yes. Okay. So a simplicial set is a collection of sets indexed by the non-negative integers together with boundary maps, lowering dimension by 1, and there are n plus 1 of them from xn to xn minus 1. These are boundary maps. And degeneracies, which go from xn to xn plus 1. Again, there are n plus 1 of them. These are the degeneracies. And they satisfy some quadratic or composition relations. But the way to think about them and the way to remember what they are is they come from the sort of paradigmatic model, which is the singular simplicial set associated to X. So here, sigma X is a topological space, sigma X sub n is the singular n simplices. In X. So it's a set of all continuous maps from the n simplex to X continuous. So usually when you do singular homology, you take this as a basis for an abelian group. Here we're just taking the set. Now what about the boundary maps from sigma of X n to sigma of X n minus 1? Boundary I is simply restriction to the ith face. So there's an inclusion of delta n minus 1 into delta n, the ith face, which sends x naught up to x n minus 1 to x naught up to x I minus 1, then 0, then xi up to x n minus 1. And here we have n plus 1 numbers adding up to 1. The standard ith face, right? 0, 1, 2. Here's the second face. Here's the 0th face. Here's the first face. Okay, so the way you get a map from an n simplex to an n minus 1 simplex is simply to restrict to the various faces using the canonical identification of those faces with a simplex of 1 lower dimension. The degeneracies, Well, what is the degeneracy SI of sigma mapping delta n into X? It's the composition with a collapsing map of delta n plus 1 to delta n, a simplicial map that repeats vertex I and I plus 1. So SI sends Vj into Vj if j is less than or equal to I, and sends Vj into Vj minus 1 if j is greater than I. That's what it does. These are the vertices. That's what it does on the vertices. And then you extend simplicially. So for example, the degeneracy that we're talking about from 0, 1, 2, S1 would go down to 0, 1. 0 goes to 0, and 1 and 2 both go to 1. Okay. S naught, 0, 1, 2, would send 0 and 1 to 0 and 2 to 1. Okay. And then give the map from xn to xn plus 1 is just composition with these projections. Okay. So you have to say which vertex, there's a pair of vertices that are going to get collapsed together, and they will be vertex I and I plus 1. You just compose with that map. So you can imagine their various relationships. If you take two boundaries, well, you'll put in two zeros here, and you could do it in two different ways. And the formula, I don't know if I have the signs right, but it's something like di dj is dj minus 1 di if, I don't know, j is less than or equal to I think. There's formulas like that, similar formulas for compositions of the SI and formulas for composing the SI and the boundaries, various quadratic expressions like that. And they all come out of what's true in this special case. Just look at what's true in the special case, and that's what's true in the general case. All right, so that's the simplicial set. If we have a continuous map from X to Y, obviously there's an induced map from the singular simplicial set of X to the singular simplicial set of Y, sigma of psi. Given a simplex in X, you just compose. And that's a map that preserves all this structure, the face and degeneracy relations. So it's a morphism of simplicial sets. Okay. And the image is a simplicial subcomplex, sub-simplicial set, I guess I should say, is a sub-simplicial set. Because if you have a simplex here, an n-simplex that's in the image, all of its faces are in the image, and any degeneracy is in the image because this map preserves faces and degeneracies. Now, we're going to apply this to the map rho from the continuous map from embeddings to these paths, elementary paths. So we have a continuous function there. We got an induced map from sigma p into sigma, this is an E, EL. And by definition, sigma, well, by definition, what I'm going to call EL tilde is the image of sigma of this map rho. So a simplex so this is a simplicial set, and a simplex of EL is a map from delta n, continuous map delta n into EL that can be lifted. To some sigma tilde mapping delta into P. So it's just all the simplices in EL that can be lifted. So if you think about what's happened to pi naught, I did this last time, but I'll say it again. Pi naught of EL is the points of EL with an equivalence relation. X is equivalent to Y if there exists a path I in P such that rho of rho mu of 0 is X, rho mu of 1 is Y. So that's different from the equivalence relation that would define pi naught of the space, which is just the points of the space mod the equivalence relation. X is equivalent to Y if there exists a path in the space with these properties. So if this were a reasonable space, or if this were a reasonable map, for example, if it has local cross sections, then these notions would be the same. But in fact, this map turns out not to be so reasonable. It doesn't have local cross sections, and these are different notions, and we have to work with this one. And so the theorem is that chi mapping EL into the descending disk space induces a map, chi star, shall we call it, from this subsimplicial complex made out of the elementary paths into the simplicial set, a singular simplicial set of D. Now, when you have any reasonable space, well, the simplicial set is, in a very strong sense, homotopy equivalent to, weakly homotopy equivalent to the original space.
Excuse me, what was EL twiddle again? I forgot.
It's the underlying, it's the
image of the.
Yeah, so you take EL, you take its simplicial set, the singular simplicial set, so all the simplices that map into EL, and you only look at those that are images of simplices in P.
Okay.
So you've changed, you have the same underlying space, but you've in some sense screwed up the topology because you're looking at fewer, you're considering fewer simplices, and you're going to take the homotopy type of that simplicial set, and you'll probably get a different homotopy type. So it's not a function only of the space, it's a function of the space and this map. But we're only going to be worried about, so
it's like only paths that come as images of.
That's right. So we're going to be deforming these. An element in EL is a path, so we're going to be deforming a path, but we don't allow an arbitrary continuous deformation of that path. We only allow deformations that are covered by deformations by embeddings. So you take a deformation of the embedding, and then you, to each element to each embedding in the family, you have one of these paths, and you take those paths of paths.
I see.
Right? So it's a subsimplicial set, and we're really only interested in pi naught in the end, so it's a subcollection of paths inside EL, not all paths, only those paths that can be lifted to paths of embeddings.
Okay,
so they're closer somehow.
You want to consider, right? Because
right.
We want to get to a path of embedding.
That's right. So I want these paths not only have to be deforming continuously, they have to be, you have to be able to embed them in a whole continuous deformation of these embeddings of the standard neighborhood. So just because they happen to be close, but they didn't come from nearby neighborhoods, I don't want to think of them as close anymore. So in some way, I'm changing the topology. I'm certainly changing pi naught by doing this. But if you have a simplex in EL that can be lifted to the pass to the embedding space to P, then you can take that lifting and push it down and get a simplex in D. And if you chose a different lifting, well, it differed by this group element, and the group elements act trivially on the descending disk, so you get the same image. So there is a well-defined map across here from this sub-collection of simplices into the simplicial set for D. And the theorem is that map induces an isomorphism on homotopy groups. So that's the, oh dear, that's the first part of my bridge. Where was my bridge? Where is my bridge? It's a long time ago. Missed it. Yeah, here it is. So this is our bridge. This is the first part of our bridge. We're getting, in some sense, halfway there from the, it actually goes in this direction. The elementary paths lift to embeddings. Embeddings have descending manifolds, and that's the map from these elementary paths to descending manifolds. If you have one of our restricted paths of paths here, that lifts to a path of embeddings and therefore gives you a path of descending manifolds. If you just had a continuous family of elementary paths, you would have no way to construct a continuous family of descending disks because you need the whole model to get the descending disk, not just the elementary path. All right. Well, unfortunately, I'm back to where I was at the end last time, and I'm running out of time here. Okay, I have to tell you, yeah. So remember that this group G12 acts on embeddings. So this is the group, remember, automorphisms of the model that preserve norm x squared and norm y squared. So it acts on P and acts simply transitively on the fibers of this map rho. So that was the lemma, that if you have two elements in P that have the same descending path, then they differ by one of these automorphisms that fixes the norms of x squared and y squared. And this is clearly a free action because you're talking about embedding. So any non-trivial automorphism of M gives you a different embedding. Non-trivial diffeomorphism of MR gives you a different embedding. So it's simply transitive action. If this were a reasonable map and had local cross sections, that would say that P was a principal fiber bundle over EL. The fiber would be the group, and you'd get a homotopy long exact sequence from the fibration. So if you had local sections for rho, this group action would make P a fiber bundle over the base, and you get a sequence like that. Well, we don't have local sections, but replacing EL by this sub-simplicial set, quote, gives us local sections. I mean, we've changed categories, so it's not quite a local section in the usual sense, in the sense that any A in EL tilde N, any N simplex in EL tilde has a lift, as many in sigma P. So if you think of cross sections, well, we have cross sections over every simplex. This would then be a cross section. Here's P, here's E, here's a path in EL, so an element in EL1, and we have a cross section, A tilde, projects down to this. So we forced cross sections, and what happens is we get, in fact, there is a homotopy along exact sequence. Pi I of G12, pi j of P, based at phi, into pi j of EL tilde, based at rho of phi, and you continue. So you use the fact that we have some simplicial analog of a locally trivial vibration, and because we've built in this cross-section condition, that has the homotopy theory of a locally trivial vibration. So you get a long exact sequence. Of course, this is a simplicial set of P, not P, and this is a simplicial group associated with G12, not G12, but they have the same homotopy type, so the same homotopy groups. So you get an exact sequence like that, and you compare it to the exact sequence Pj of P phi down to Pj of B. This is a vibration, so I don't have to do any of this fancy stuff. And the fiber here is P. So these are the embeddings. These are embeddings that give the disk. These are the embeddings. Well, these are the fiber. So nu is in B, and this is simply in B. This is simply the fiber over B. So you have two sequences that cross. You have this horizontal sequence, ij of G12, ij of P phi, ij of EL tilde, and this one is ij of P nu down to pi j of B, and it continues. It's an elementary exercise to prove screwed up something here. I'll see what I'm supposed to have. Yeah. All right. Yeah, I have to consider, okay, I'm gonna have to pick it up here. So I claim that in studying this homotopy exact sequence and this homotopy exact sequence, comparing these two, you see quite easily, to just a diagram chase of a couple of diagrams, that these two homotopy groups are the same. But I'll have to do that next time because I've run out of time. All right, well, I guess this was mainly a review. We basically got back to the same point I had arrived at on Monday. Next Monday, I will prove this theorem, and I'll talk about the other half of the bridge, which is actually quite a bit simpler than this. It doesn't involve any of this funny simplicial sets, except the same simplicial set here. All right, well, I have to quit, so.
Bye-bye. Thanks.
So long. Yep.
Well,
See you on Monday.
see you.